So again, welcome to our webinar, Advantage for Business. I'd like to introduce our two speakers. Our first speaker is Murray Tom, who is Vice President of Software and Cloud Services at D-Wave. He's responsible for the LEAP Quantum Cloud Service, our Ocean Tools, system software, and our documentation team. Previously, Murray led a team engaged in customer projects related to algorithms, applications, and performance testing. Since joining D-Wave in 2002, Murray has been involved in all aspects of systems engineering and processor development for D-Wave's quantum computers. Our second speaker is Mark Johnson. Mark is Vice President of Processor Design and Development and Quantum Products at D-Wave. He received his PhD degree in physics from the University of Rochester. Mark joined D-Wave in 2005 with several of his TRW colleagues around the time D-Wave was turning its focus to developing quantum annealing based on superconducting flux qubits. And Mark is the Advantage product owner and led the team who developed and created the Advantage product. So with that, I would like to turn it over to Murray.
Thanks, Susan. Just a quick voice check. You can hear me okay?
Yes, you sound fine.
Okay, perfect. Well, hello, everyone, and thanks so much for joining us for our webinar today. It's delightful to see so many of you who have logged on to hear us talk about the Advantage system. So yeah, as Susan was mentioning, on September 29th, 2020, we launched the D-Wave Advantage quantum computer. And it's the sort of most connected and powerful quantum computer in the world today. The presentation we're going to be giving you, we're going to be talking about applications that customers are building on the LEAP cloud service with the Advantage system available through that cloud service. We're going to talk about the Advantage system itself, the new innovations, the sort of advanced superconducting fabrication, and the resources in terms of qubits and connectivity that are available to you as you're building applications. And then we're going to talk to you about our LEAP cloud service and how you can get access to it today and what some of the features are in the system design to make it easier for you to build your first or second or nth quantum computing application. The first thing I want to say is that D-Wave is a company that's been focused from the very beginning on helping customers get advantage or get business value out of quantum computers as early as possible. There are a lot of different ways to build quantum computers, and there are a lot of different things we could potentially use them for. But if quantum computing as an industry is going to be successful, it needs to be able to provide value to business customers at each stage along the way. So each quantum computer, as it's developed, provides value to users. It increases the use cases and improves the performance advantage. And that's really central to all of the work that we do at D-Wave. I got involved in quantum computing 18 years ago, and I was really excited to sort of like see the systems come to reality and see their use cases. And in that time, I've talked to a number of folks, but particularly most recently, as I've been out talking with developers and business owners who have applications they want to be able to run on a hybrid quantum classical systems. The reaction I'm getting, while many people ask me what quantum computers are and how they're built and how the technology works, there's a much larger proportion of people who have sort of told me, if I knew what quantum computers were used for, I'd be more interested to learn about what their capabilities are and how they function. So that's what we're going to start right away with, is talking to you about some of the companies and the applications that they're building on our quantum computers right now. And it's important for me to say that D-Wave is the only company in the world that has a quantum computer that can support today's real-time business applications. So if you are serious about incorporating quantum, classical, hybrid technologies into your business applications, this is the place for you. I'm going to start by talking about Mentonai. This is a drug discovery company, and they are focused on designing proteins for medical treatments computationally. So rather than taking existing proteins and chemically modifying them and then testing them to see if they respond well in certain conditions, this is actually looking at a medical challenge, absolutely like full information about, okay, what is the structure of the the virus that I might be trying to target here? How might I design a brand new protein where a calculation is actually determining the place in the sequence of amino acids that are going to then fold and function in exactly the place where we want them to. The company has actually developed a technique to allow them to use a quantum classical hybrid programs to determine these calculations, and they've actually seen value in their operations here. They've actually designed proteins that have been computationally validated and are proceeding through chemical synthesis so that they can be advanced to live virus testing against COVID-19. The second company is Save On Foods, and Save On Foods has been seeing excellent early results in optimization for the grocery industry. Now, for those of you who don't know, Save On Foods is a Western Canadian grocery retailer, and they would describe themselves as sort of like a mid-sized grocery retailer, except that their business has actually got a lot of the complexity to it that many much larger organizations have. They have an online site with e-commerce and the ability to do grocery deliveries. They have their own product line within their stores. They have pharmacies. They have coffee kiosks with Starbucks. Their operations are across 4 different Canadian provinces and territories, which means they have to cover in their transportation and logistics 3 million square kilometers in an area where it can snow at any time of the year. They can have flooding conditions or they can have desert-like conditions. So this was a really exciting project where they were actually able to take an important business logistics problem that they had and reduce the time the task took from 25 hours to a mere 2 minutes of calculations each week. And this is important because it's taking 4 million decision variables that they're working with and allowing them to take into account business interactions that are going to simplify their business operations and make it easier for them to deliver the important and critical services to their customers. And what was really exciting with talking with the Save On Foods team was that this was a departure from the notion that using quantum computers is a research experiment. This wasn't a measurement that we were going to do, one time a year and write a paper on and publish. This allowed them to see the fit within their own business systems to be able to operate on a monthly, a weekly, a daily, or an hourly basis. And that's I think really captures the vision here of what everyone in the quantum computing industry wants to see happen with this technology. Denso is a major auto parts manufacturer located in Japan, and they were using our Advantage system to investigate a vehicle routing problem, which involves transporting items to particular locations at particular times. So they're taking into account not just the paths that the deliveries need to be able to take, but also taking into account that different paths occupy different periods of time and trying to factor in the delivery periods that were acceptable in terms of when the parts would be arriving in these different locations. During our Advantage beta tests, they were able to run experiments and tests for application problems that included 44,000 logical qubits. And this is really important because the notion here is that as quantum processors develop, they're getting larger, they have more interconnectivity and more qubits, which allows you to program a wider breadth of applications. But no quantum processor is ever going to be large enough to actually occupy the entire problem itself, which is why the quantum classical hybrid solvers that are available in LEAP that leverage Advantage are so important for tackling these business challenges. The fourth one I'll mention here is OTI. OTI is a company that develops organic LEDs for consumer products. And organic light-emitting diodes are basically sandwiches of material where it's really important to know what the light-emitting and transmission properties of the materials are. So they are doing a lot of complex electronic structure calculations. And they've been able to develop hybrid quantum classical workflows that allow them to do this and still yield precise results. And that actually reduces the iteration time that they see in the calculations that they're running, which is providing them with sort of an industrial benefit that they want to leverage as it grows. And really important to this is that part of what they're doing is enabling themselves to get a benefit today from the quantum technologies that are accessible through LEAP. But also by designing these hybrid workflows, they're setting themselves up so that as the technology grows and develops, there are leaps in performance that get yielded as the new technology comes out, kind of like you'll hear Mark talk about as he's describing the Advantage system. And they already have their application programs set up to adapt as those changes take place so that their applications get the benefit of that technology disruption. There's sort of the disruption in terms of the jumps in performance, but not any disruption in terms of their application operations. They can continue running their programs as these technologies advance. Okay, so let me talk a little bit about, those different applications we were talking about were from material science and medical research and business logistics and operations. Quantum computing is really a horizontal technology. It has a computational ability that can be applied in many different places. And what that's causing is a major advance in the quantum computing industry. And the Advantage system is at the forefront of that maturation. So we already have quantum computing systems on Advantage that are, we already have commercial applications that are being supported by this Advantage system. In our LEAP Cloud Services, there are over 15,000 developers who are logging on to learn about what are the programming techniques, looking through the searchable examples, building them and adapting them to their own applications using the online IDE. We've seen entrepreneurs who have started up companies and built their businesses around the kinds of new capabilities that quantum computing is going to provide. Large companies like Accenture, as service providers, they're training up new teams so that they have the expertise and knowledge about what this technology will provide, because their customers are asking for help in terms of building applications that can be quantum hybridized and set up to take advantage of the new technology that moves forward. And they need that help from those professional services organizations to help guide them through what the potential changes are in order to gain the advantages and avoid the pitfalls. There are a lot of major cloud services companies that are moving into this space as well. And AWS has launched their Amazon Bracket service, which includes access to D-Wave quantum computers and the Advantage system. So for users there, they can get access to our quantum computers as well. And AWS really told us the reason for them to take this and make it generally available this year is because their customers were ready. They were asking for the opportunity to begin testing and building and programming quantum computers in real-time business application contexts. And they really felt like it was time to basically make that available. And also, there are universities and incubators like the University of Toronto's Creative Destruction Lab that are producing quantum startups. They actually have streams which bring in entrepreneurs who are excited about their new ideas and how to leverage this emerging technology with the domain expertise that they have, and connecting them with business leaders and investors so that they can get their new company started up and get their products on the market and be able to take advantage of the technology with the knowledge that they have from that program. And market research, 451 Research has done interviews with hundreds of executives from Fortune 5,000 companies in order to find out, how ready is the market for quantum computing. And not surprisingly, they found that nearly a third of companies have abandoned some complex problems in their companies because of the time to solve. And I think we can all relate to, circumstances we have in our businesses where we've got some great ideas and we know we want to proceed, but either because of limitations in the technology or where we are in our product development, it's just a little bit beyond our reach. So I think it's natural to see that 4 out of 5 companies, when they look into their businesses, they have quantum use cases in mind that they want to see applied in the next 3 years. And in fact, 2 out of those 5 have already begun experimenting with quantum computing today. And they told 451 Research the primary driver for that is competitive advantage. They are ready to do very fast technology adoption because it's really important for them to be able to carve out every advantage that they can. And the benefit that they're expecting from quantum computing is going to be increased efficiency. So with that, I hope I've kind of given you a context of, what kinds of applications users are using. And that's just sort of beginning to scratch the surface. And also, it's not just that people have begun using applications. You can actually see all through the industry that players are moving in and positioning themselves so that they can help their customers and begin using quantum computers that are available right now. So what is the overall roadmap? Where are we in the history of quantum computing? Well, in the past 20 years, quantum computing has been, a very theoretical, complex area that's really only been available to a small group of scientific researchers who have been investigating the system and programming it. Now at D-Wave, we commercialized our systems 10 years ago, and really a large user base got involved in studying them, de-risking them, developing techniques, and actually building early applications on the system. And so as a result of that work and that background, 2 years ago, a group of researchers from NASA Ames and from the University of Texas, they were funded by the US government to develop classical techniques to compete with quantum computers in order to be able to really get a strong sense of like how strong are the quantum computers, what are their capabilities. And they were able to find test cases where the quantum computers were 100 times faster than that whole suite of the best classical heuristics they developed. And 1 year ago, D-Wave published results in Science and Nature with a follow-on study, which showed that you can actually do quantum material simulation work and yield speedups that are 3 million times faster than the best classical heuristics for that type of application problem. So that's really, I think, what people are very much excited about is, knowing that those kind of performance enhancements are possible, where there can be an inflection point where at one point you're using supercomputers to do your calculations, and then in a short span of time, really the only way to solve your problems with a quantum computer. Customers are getting involved, starting to do research into those 250 plus early applications that have been developed on the system in order to find their business value, and also in the hopes as these systems develop and the algorithms develop to work towards scientific demonstrations of quantum advantage in applications. So with that, let me pass it over to my colleague, Mark, who will tell you more about the Advantage system and the features that it has.
Hey, thanks for that, Murray. Yeah, I always find it inspiring to, I should introduce I'm Mark Johnson. Susan mentioned my name earlier. I want to say I always find it inspiring to hear about all the different applications that folks are trying out on our technology, and to see that we're getting into an era where really a lot of folks are actually getting value or starting to get value out of them over a wide range of verticals. That's one of the things I find inspiring at the Qubits user group meeting, which Susan alluded to earlier, and I think we're going to mention again at the end. You can actually, Murray mentioned a few examples, Mentonai, Save on Foods, Denso, and OTI, but you can, later at your convenience, you can log in to get signed up and log in and go and check out all of the talks, all of the much wider array of applications. I want to spend a little bit of time this morning talking to you about what's under the hood, what's the technology that enables these new applications. I want to make a point that it's not necessary to know a lot of the details about the technology to be able to use it and apply it. Well, one doesn't need to know quantum mechanics or understand it to be able to use the technology. But I do want to spend a little bit of time talking today about what's under the hood and what's basically gotten us to the point where we are now, where we can start to solve problems at the business scale. So the at the core of the technology, there we go. The core of Advantage is a new superconducting quantum annealing processor that has more than 5,000 qubits, 35,000 interqubit couplers woven together in a new qubit architecture that's basically got 2.5 times the interqubit connectivity of any of our previous commercial product generations, including the most recent one, the 2000Q. And at the core of that new processor, and actually all throughout the product, there's a central idea which is basically to be able to solve larger, more complex problems that are at a scale that's relevant for business. I think Murray touched on this point that, Advantage really is the largest and most powerful quantum computer built to date. It's live in Leap and has been for our quantum cloud service, and has been since we launched it at the end of last month on the 29th. And you can log in now and get free time on Leap and check it out if you haven't yet. Before you do, let me tell you a little bit more about it, and let us talk to you a little bit more about what's going on and how we got here. So there we go. At the D-Wave has always taken a practical approach to quantum computing. Always trying to think about whose problems we're trying to solve and understand, which problems businesses care about. I'm showing here a plot in orange dots over the course of years on the x-axis, the size of demonstrated quantum annealing processors. On the y-axis, with a log scale showing the number of qubits plus the number of interqubit couplers for each system as a measure of the size and complexity of the processor, but also, giving you some sense of the size of the problems that can be solved. About a third of the way along here in 2011 was the D-Wave 1, which was our first commercial offering. A little bit further up there towards the top, you can see the 2000Q product. And then at the very upper right is Advantage, which is what I want to talk to you about this morning. This has been a long time in the coming, and a lot of us have been working on this for several years. I want to make a point here, though, is that over the course of basically the last 10 years, we've been able to get a lot of really good user feedback, customer feedback on the use of our systems, and we've distilled that feedback down into a few key principles that underlie or the foundation of the design of this current product, and I'm gonna touch on those going forward. And the basic idea, though, is to be able to solve larger and more complex problems. So folks, the real problems that folks encountered have lots of variables, more variables than are typically fit into quantum. That's the challenge, that the problems are larger than the scale of available quantum computers. So this generation of system Advantage has 5,000 qubits, up from 2,000 on a previous generation. Real problems include a lot of complexity, which means interactions or constraints between variables, and that means more interqubit couplers. And so towards those and towards addressing those, we basically updated the topology. And I'm showing you here sort of a schematic representation comparing sort of our previous generation topologies and the current generation. These are schematic representations of subsets of the processors. So on the left here is the Chimera topology. The orange dots on this are representing individual qubits, and then the blue lines connecting the orange dots are representing interqubit couplers. And this is a fundamental characteristic of this topology, this sort of method for connecting qubits together, is that each qubit is connected to 6 other qubits. And over here in the middle of the chart, we're showing a schematic of Pegasus topology. That's a small subset of our 5,000 qubit processor. And again, orange dots are representing qubits. The blue lines are representing interqubit couplers. And admittedly, when this way of looking at it, it's a bit harder to follow what's going on. But the main point is that each qubit is now connected to 15 other qubits. So that's 2.5 times the connectivity in all our previous generations. And that was the main point that we were going for. To talk a little bit more about, I'll talk a little bit more about what that means. But before I do that, I would just want to touch on a point, is like, how did we how did we do that? What was the sort of enabling technology? Essentially, it was a significant increase in the fabrication complexity. So remember that this core of our technology is a superconducting integrated circuit chip, and to enable the higher connectivity and the larger number of qubits, more couplers, we basically redeveloped the fabrication stack from the ground up with new materials, new processes, significantly more complexity. And just so as a measure of that, the active element of the sort of active device of a superconducting integrated circuit process is the Josephson junction. And you can think about that as analogous with the transistor being the active element in a semiconductor process. So Josephson junction, so in our previous generation 2000 Q product had about 128,000 Josephson junctions. And with the Advantage product, the 5,000 qubit processor has more than 1 million Josephson junctions. So this is way outside of what folks have done with superconducting integrated circuit technology. So a very, very large scale of integration. And that basically allowed us to get all of these devices into a relatively small area. Just to give you a sense, though, what does that mean? So Murray alluded to the work that came out a couple summers ago in one in Science and one in Nature. And the publication in Science magazine, Richard Harris et al., was a described quantum simulation of cubic icing spin glass lattice. And it was actually an 8 by 8 by 8 spin glass in a cubic lattice. And that's basically the largest lattice that we could embed in the 2000 Q product. And I'm showing that sort of pictorially here on the lower left of the chart. You can see that sort of a representation of that. With the Advantage product, with the more qubits and particularly with the higher connectivity, we can embed a 15 by 15 by 12 lattice, which is actually about 5 times the size. And that's shown here just to the right. So it's really about being able to solve larger problems. There's something that you can't see in this representation that I'm showing here that's really quite important, which is that in the 8 by 8 by 8 lattice that was embedded on the Chimera and the 2000 Q product, each node here, each virtual node in the lattice is represented by 4 physical qubits. But in the implementation and Advantage, each node only needs 2 physical qubits to represent it. So it's a larger problem, but it's also embedded more compactly. It's a more efficient embedding. And the fundamental point here is that a more compact embedding or compact representation of a problem basically translates into higher performance for quantum annealing. So you've got larger problems, more complex problems represented more compactly, and that gives us better performance. So I want to sort of show another view of that here. This is an example of another, and this is sort of an abstract representation of a problem, but a typical QUBO problem might be represented graphically. So QUBO is quadratic unconstrained binary optimization. I'm showing here in the middle of the chart, where again the dots here, the different colored dots now representing in this graph logical variables of a problem, variables in your problem, and then the lines between them are representing sort of constraints or interactions between those variables, clauses between the variables. And then on the right is a representation of how that might get embedded or mapped into the physical hardware and in fact, for example, there's software to do this in our Ocean tools. So this is not something you're necessarily doing by hand. I mean, you certainly could, but we have software that sort of helps with this. And the way the mapping might work is showing here with the red circle showing how one logical variable gets mapped into a series, in this case 3 physical qubits. that are laid around in different parts of the processor. And again, so the graph on the right is a physical representation in the sense that each dot here represents a physical qubit, and each line between them represents a interqubit coupler. So this is showing sort of schematically, pictorially, how mapping a problem that looks like schematically in what's shown in the middle of the chart, it gets embedded in a certain way. And so a given variable might get mapped into a few physical qubits. And here the point is, and this is a specific example, is with the Advantage processor. But the point here is that the higher connectivity, because of the higher connectivity, because each qubit is connected to 15 other qubits in this, whereas in the previous generation, each qubit was only connected to 6, that we find that typically the embeddings are more compact, so there are fewer physical qubits required to implement each logical qubit. And that's typically, it varies how much of a ratio that is, how much more compact it is, depends a lot on the specific problem. But on average, it's somewhere between 2 to 4. And it just, but it'll depend on the specific connections of the problems. And there are a few reasons why that more compact embedding actually buys you higher performance. Both the fundamental quantum annealing characteristics of quantum annealing, that the dynamics are more efficient for a smaller number of physical, say chains, smaller chains. But also it allows you to sort of reduce the dynamic range that you're requiring. So you don't necessarily need as strong of an intra chain coupling to hold the chain together. I just want to give another sort of color, a picture of this, is that, so really the hardest problem to embed is a fully connected graph, or it's at least in some sense the most challenging. Maybe it's not the hardest, but in some way it's the most challenging. So a virtual graph where of some size where every qubit is connected to every other qubit. And we're just showing here an example of how we're doing with the Pegasus, the new degree 15 connectivity graph that's implemented on our Advantage processor as compared with the 2000 qube processor. And so the plot here is giving us a sense of that. On the y-axis is the largest clique size. So clique is another name for a fully connected graph. That is a collection of nodes where every node is connected to every other node. So the largest clique size, how many nodes there are that are fully connected. And if you look at the blue sort of staircase there, the x-axis there is showing the chain length. That is, and this is sort of another name for how many physical qubits are needed to represent each virtual node. And per the comments I made on the previous chart, the more that you need, the more challenging the more challenging the performance is. And the shorter the chain length, the more performant one ends up getting. So here you see the blue staircase is showing how the max chain length or min chain length increases as you try and embed larger and larger clique sizes. And the basic point here is in the orange staircase is showing that for the Advantage technology for the Pegasus graph, that we're getting substantially about a factor of 2, a little bit better than that, factor of 2 increase in the size of the clique that can be embedded at for the same chain length or same virtual node size. Actually, and then there are really 2 ways of looking at this. If you look at the horizontal red arrow there, that's showing that at a fixed clique size, an Advantage, you can embed it much more compactly. The 64 node clique, you can embed that with a chain length of 7 in this example. Or you could say, okay, if I have a chain length of 17, I could, instead of embedding a 64 node clique on the 2000 qube product, I could actually embed something like 120 node clique. So typically you would be somewhere in between those 2 extremes. So you can either embed a much larger clique with the same interconnections, or you can embed the same size one much more compactly. This is one specific example type of graph we're showing here, and you can, I think, find this in the white papers on this for other types of problems, not all equal 3-sat. And we talk about 3D lattice here. And so really, of course, well, the one that matters is the specific problem you have, which may or may not be a regular graph. But the tools that allow us to take a particular graph, that allow you to take a particular problem, a set of clauses, a set of interactions between variables, and map it into the hardware available in the Ocean tools. And you can go and try that out and explore that as well. So stepping back, the reason that we're doing all this is that we want to be able to solve larger and more complex problems. And so the question is that how well are we doing that? So let me just dig into a couple of examples here. So I want to just do a quick. Perfect. Yeah. Just a quick time. Just a couple of examples here. So here we're showing in these two plots. We're showing problem performance. We're running about 10 sample problems of types I'll mention in a second. And the left one is our cliques, our fully connected problems with random couplings chosen between them of different sizes. So from say a K10 all the way up to a K60, what's being plotted there? So the X and Y axis are both plotting residual energies on a log scale. So the larger the residual energy, the weaker the performance, relatively speaking. So the further to the left you are, or say the further down you are, smaller residual energies means better performance. And what's being shown on the y-axis there is the residual energy for a particular problem when run on advantage. And what's being shown on the x-axis is the residual energy when it's run on the 2000Q product. And if you were on the line, there's a line, slope 1, going up the middle there. And that's basically a line where the performance is equivalent on both. So that's a tie. And so the fraction of problems, and each dot there is basically the median, is the median performance in both cases. So the fraction that are below the line are basically cases where we're getting better performance with the advantage technology, and the fraction that are above the line is showing better performance on the 2000Q. And so here we're seeing that we do overall get a performance increase with the new technology, and that's really from the higher connectivity turning into more compact embeddings. And then there's a similar plot showing improved performance on not all equal 3-sat, right at that cusp of clauses to variable ratio. And then maybe I'll just make another point now. It's a really important point. So part of this, what I've talked to you about for the technology, is making our underlying QPU so that it can actually, the quantum processing unit, so that it can embed larger and more complex problems. But that's just the starting point for trying to get up to the scale of business problems. A really important part of our approach is around hybrid computing. And we believe really that the most the first applications, and we've now seen this because we've seen such applications, that quantum applications that give value to customers are going to be hybrid, and they're making non-trivial use of both quantum mechanical and classical computational resources. And so this is sort of a very simplistic example of showing how doing some simple post-processing, which you can actually access, I think, in this example in the Ocean tools. So what we're showing here, sort of on the for both Advantage and the 2000Q in orange and blue respectively, sort of residual error is this analogous to the axes that we were showing previously. This is just on the y-axis versus clique size, and again for sort of random problems of different sizes. And when at some point, so then we're showing that so the higher you are on this plot, that's showing performance degrade. When you're on the bottom at 0, you've got ground states, and as you increase the size, you get more and more possibility that a particular virtual node will actually come back broken. That it will say not all the spins will be pointing in the same direction. And if you just interpret that as a failure, then in this plot that's not shown. So this is showing going up to on the left plot, we're showing the largest size at which you can get sort of viable answers for the two products. And in fact, you get good answers at a much higher click size. But it's actually a very straightforward matter of post-processing, so very computationally inexpensive, of simply assigning majority vote, doing a majority vote on each virtual node, the constituents of each virtual node, to decide, whether that virtual node is spin up or spin down. And then you can get good answers all the way up to the maximum size that's embedded. And you can see this gets you some benefit with the 2000Q product, but actually pulls you all the way up to getting good performance all the way up to the full scale that's embeddable at for the Advantage processor that we're looking at, which is just over 120 nodes. So this is the most simplistic approach, example of hybrid algorithms. But in fact, we're further, and I think Murray's going to be talking more about this, in our Leap quantum cloud service, have a number of hybrid solvers that do a lot more for you and are using Advantage. So maybe with that, I'll pass it back to Murray, and he can tell us about Leap.
Thanks, Mark. That's terrific. Just needed a second there because I had like 3 mutes activated just to make sure I didn't interrupt you while you were talking. So I hope that we've been able to convey, the breadth of the applications that people are using it for, and some of the excitement, I think, about the idea of being able to use quantum computers in application, as well as just how novel and complex these programmable quantum computing systems are. I mean, it really is this point in history where humans have the ability to understand quantum mechanics and how it can be leveraged for useful work in a way that's never been possible before. So I'm just going to finish our talk quickly by telling you how you have access to these services today through Leap. You can actually go to, just search D-Wave Leap in your favorite search browser. You can go to our website or to Leap itself and sign up, and then you'll actually see you'll have access to all these services in the system right there. Leap is the place where all of D-Wave's products come together in terms of providing access to our users. So this includes the D-Wave Advantage system and any of our quantum computers which are online. It's cloud-based, so it's convenient. You can access it anywhere where you have access to the internet. And this is the only quantum computing system which is up 24 hours a day, 7 days a week. You can get real-time access. You can submit problems and get immediate answers back. And we have a user interface which includes a dashboard, a whole series of resources, learning resources and tools resources. We've got the Ocean open source software SDK with programming concepts available through Leap to sort of teach you the skills you need to be able to program. There's an online IDE in Leap, so you can actually go in and start programming your first examples yourself. And there are a set of open source searchable examples to help get you started. And we've also got a help center which provides federated search across all the materials we have on system documentation, Ocean documentation, and the examples that we've been building, as well as a community forum where you can post questions for one another, challenges, ask questions of the community, because each of us is a teacher and a learner. We're learning about quantum computing, we're learning about the things that it can offer, but we're also teaching one another by bringing our math skills or our physics skills or our application domain expertise to that community and posting, novel ideas about, how to approach important, challenging problems in industry today. The Leap system, you're going to be able to get access immediately. You'll see the Advantage solvers. You'll also see both the hybrid solvers that we have in the system. The Ocean open source SDK is going to prefer to use Advantage the moment that you start programming it. Any of you who have existing programs, you'll see that it will switch over automatically to the new system. And our hybrid solvers are developing and expanding, and we're actually going to continue to develop those and release updates to those solvers in Leap that leverage the things we learn about what this new technology can provide as we get an opportunity to operate it more. Now, I'm just going to cover some of this material briefly here because I see some fantastic questions in our Q&A forum. The hybrid solvers in Leap, this is not about simulating a quantum computer to determine what it can do. This is about using classical computers like CPUs and GPUs alongside quantum computers, which are quantum processing units, QPUs, to get you the best results possible in a business application context. We have expanded our second version of our binary quadratic model solver. This is one that handles variables that are either true or false, yes or no, purchased or not purchased, up to 1 million variables. And that's not because we're expecting each of you to have a problem that's 1 million variables in size, but it's to give your teams, your businesses, yourselves as developers, the opportunity to just have the room to build applications at full scale and test on production data. We've also included a new hybrid solver called a discrete quadratic model solver. This allows things beyond binary variables. Think about dice rather than a coin flip. So you can actually now optimize choices such as like choose one of 11, 19, or 29, or choose one color of red, green, or yellow. This is going to allow discrete multi-level variables, and that's going to be really important for some applications where the context is one from a set of choices. And it'll allow you to formulate your problem for quantum computers in a way that's closer to the way the problem exists in the real world. And that's really what this is about. So, with hybrid solvers, this is about allowing yourself, your business, your application to benefit from the advanced performance that quantum computing provides without the disruption of having to choose just the right moment to use it. Because you can get all the benefits and flexibility that classical computing provides alongside the quantum processor. That is going to give your team time to see how it fits into the organization, explore the problems it can be suited to, learn the programming techniques, and basically see it used in application before having to dive down into the details of, okay, how do I learn more about the performance tuning of the quantum processor parameters itself? With this new hybrid solver service, we're going to be allowing bigger inputs to provide better solutions. So in this graph on the left, we see on the x-axis the number of nodes. So we're going to be jumping here from 10,000 variables up to fully 1 million variables accepted. And the total weights that can be accepted are going to be going up to 200 million. So in this second version, we're going to be allowing sort of this extra space that's defined in the graph above this lower gray line in terms of the types of applications that can fit in that domain. In addition to that, we've made changes to the algorithms itself. So on MQLive, which is an open source repository of problems of this type, we've actually picked some of the largest, sort of most application-focused problems from that data set. We published it online, so you can see those, review them. And we've run these hybrid solvers on those instances, competing against 27 other solvers that are available there, and beating them or tying them in 84% of the cases. And you can see by the orange and yellow colored bars that this is a substantial improvement over the previous version, the first version of the hybrid solver service that we had provided. With that, I hope we've been able to convey some of the excitement about this new, more highly connected, more powerful quantum computer built for business. The fact that you have access to it right now with the ability to submit problems to hybrid solvers, instances of up to 1 million variables, that you'll have room to actually support and build real world applications that can leverage quantum computing. We hope that you'll be one of the first with access. If you go to cloud.dwavesys.com/leap, you'll be able to sign up and peruse. For those of you who already have accounts, you'll actually see that you already have access to the Advantage system there. Some of our tools and examples are already programmed the system. You'll be able to see how to run it there. And for those of you who are interested in checking out the presentations from the Qubits User Group Conference, the website is www.qubits.com. You can register there and then log in and then go through all of the different days of presentations, see presentations from some of the customers I spoke about at the beginning of this talk, as well as a much larger set of customers around the world, Europe and Japan as well, with some really exciting talks there. So with that, let me pause, and Susan, let me know if we've got any questions.
Okay, great. Well, thank you, Murray, and thank you, Mark. We answered over 50 questions during the talks, but we have a few that we marked to be answered live, so we will take them. You'll have to keep your answers short, given the time we have. So here's a question that came in. Should we expect better performance on Advantage compared to simulated solvers? More specifically, can we find optimal states with higher probability on embedded problems on Advantage compared to the unembedded, original, and logical version of those problems on classical simulated solvers?
That's a great question. So, and that's a very technically detailed question. So there are absolutely many cases where you're going to see better results with advantage over simulated classical solvers. But the important thing to keep in mind here is that these quantum computers are built for an application space where problems can vary very widely in terms of the complexity and what are the features that make them complex. And both classical computers and quantum computers offer different strengths to tackling those problems. It's certainly possible to pose problems which have a feature where a downhill run will always lead you to the best possible answer. And no matter how large that problem is, a very fast classical heuristic technique is the right way to solve that problem. And there will also be many, many application problems where there is frustration, where you need to make trade-offs between different constraints or different aspects of the problem that you're trying to optimize. And those will represent sort of a very rough surface with peaks and valleys where you'll find yourself in one valley, but you'll have to climb over a big hill in order to make it to another valley to find another equivalent quality or higher quality solution. That's the space that quantum computers offer the best advantage. So I think that there are lots of researchers that are interested in studying just where the two technologies get their best advantages. And in fact, that's a major area of work at D-Wave. But that's part of the reason why we've offered the open source D-Wave hybrid framework to allow you to build hybrid solvers and also the hybrid solvers that are in Leap so that you can actually get the benefit of both of those technologies without having to do several years of scientific studies ahead of time.
Okay, thank you. Next question. What is the difference between Advantage and other annealers? Microsoft, Fujitsu, IBM are developing quantum computers. That would be very good if you explain Advantage and the others. Sometimes it can be confusing.
Yeah, that's a great question. Do you want to take this, Mark?
Yeah, sure. I'd love to. Yeah, and thanks for that, Bakiri. Yeah, no, there actually are. I mean, this is a really interesting time in quantum computing. And as you point out, there are a number of very different types of quantum computers that are being developed. Even different. I don't know about a lot of other types of quantum annealers that are out there. So there are a couple points I want to make about this. One is that the basic models are quite different between, for example, what Microsoft and IBM are developing compared to what they're actually developing gate model or circuit model quantum computers. A little bit more inspired by how we use classical circuits to solve problems, to do programming, to do classical computing, whereas quantum annealing is more inspired by nature's propensity to have things stay in the ground state. So at its core, it's a very different approach. And there's a lot that's sort of written on that. But from your perspective, it's probably important to consider that right now it's a buyer's market, I think, in terms of quantum computing. And so that a lot of these folks are making their systems available online so that people can use them, try them out on their applications. So I would say, I would look at this question and say, look at it from the perspective of if you're going to go and use this, what's available and what kind of problems can they solve? And can I try my application out on it? And how well does it work? And have other people tried their applications out on these different approaches, and what have they said about that? So I don't know if it's maybe a bit of a short answer, but we don't have a ton of time.
All right, well, let's get to a few more. I read that previous generations of your quantum annealers could only represent connection weights between two logical qubits in a QUBO up to a limited precision, like 3 digits or so. With Advantage, did you make any progress in this area?
So in this, yeah, it's still the case that there's a finite precision. I think we made some important innovations, and we didn't get time to talk about that in the presentation, where we're looking to see an improvement in the precision. We expect that we should get to an improvement in the precision, but it's still the case that there is a finite precision to both the couplings and the local biases.
Okay. What might be an oh, sorry, go ahead, Murray.
Yeah, it was just one thing I was going to add to that is that one of the important features is that when you're programming problems in application, you're almost always using multiple qubits to represent a logical variable. And in that sense, the increased connectivity is going to get you a net effective improvement from this, because the relative strength of your constraints versus your optimization weights will be more favorable.
Okay. What may be an example of a problem that would not benefit from using Advantage and instead keep using the older QPU, for example, due to different connectivity?
I can probably take this one. Ricardo, the previous structure of the problems that were in like the D-Wave 2000Q are available within Advantage. So in fact, you can program those problems within the Advantage system. I would say probably, you know, we've only had access to these systems relatively recently, so there's still lots of study taking place. But I would say that natively generated problems, that is generated problems that were for the previous generation and used no additional couplers, those would probably do best on that system. But for a lot of the application problems and problems that are generated from hybrid solvers, we're anticipating that the Advantage system will be superior.
Okay. This is in regard to the Denso information. How were 44,520 qubits used for this problem if Advantage only has 5,000 qubits?
Yeah, that's a great question. The way that hybrid solvers work is that what will happen is that a classical meta algorithm will begin working over the entire problem, and then it will extract out pieces of the problem that are the size that a quantum processor can take advantage of, where it will basically look at that piece, look to reconfigure it, and then pass it back into the hybrid algorithm. So that's how quantum computers and classical computers can work together so that they can tackle these larger application problems, but also handle some of the complexity that comes along with that size and applicability.
Okay, let's take two more and then we'll have to end. Is the DQM solver newly added in Advantage or was it there in previous versions?
Hi, yeah, that's a great question. It's new. It actually was just released on October 8th. So yeah, get in there, try it out, and we'd love to hear your feedback.
Okay. And actually two short ones. Can we simulate boson sampling on a D-Wave machine?
Mark, you want to take that?
Actually, I don't know.
Okay.
I'm not sure, so we'll try it out and let us know.
Okay. How important is it to understand the underlying physics?
Yeah, I tried to address that in my talk. I want to reemphasize that point, and thank you for that question. It's not. You don't need to know quantum mechanics. You don't need to solve Schrodinger's equation. You don't need to understand entanglement to use the system. Even all that stuff is happening under the hood.
Okay, well, with that, we're going to end. We will try and send emails back to the folks who have questions we haven't yet answered. Sorry, we've run out of time, but there was tremendous interest. Thank you so much. Next month, we will be doing a webinar with the 451 Research, who's going to present the details of their new report, and we will send out information to everyone about this. So thanks again for your time, and please go try out LEAP for yourself. Bye-bye.